Hi, I'm Ahmed Farooq. I'm from the Tampere University, and I'm working in Tampere unit of computer-human interaction. We basically design multimodal interfaces for a whole host of systems and devices. And today I'll be discussing our paper, evaluating transparent liquid screen overlays for haptic conductors. Okay, let's move right into it. So basically we're targeting mobile devices. Current mobile devices use vibrotactile actuators and transducers to create tactile signals. Unfortunately, the tactile mechanism is either attached to the rear of the device or anywhere where it's suitable to place the transducer itself, irrespective of what patterns or frequencies or areas of actuation we need on the touchscreen or on the back. The touchscreen events and the haptic feedback are basically loosely connected. So the feedback is never optimized for touch contact points. The actuator is designed basically for the non-dominant hand, as I said. And therefore, the disjoint between the touch points and the feedback can always compromise the haptic feedback. The current transducers also are not designed to stimulate skin receptors, which basically means that the frequency that they're generating is not necessarily the optimal frequency for the receptors to be excited. And in traditionally haptically noisy environments, a certain frequency that basically actuates the whole device can be restricted or inefficient. So to circumvent that, we basically increase the signal itself, the amplitude, or the frequency. Either of those two results in erroneous selections and something that is not useful for the screen, the skin contact. So like I said, essentially vibrotactile frequencies are limited by what we can feel or what our skin can feel. Therefore, if the signal frequency is not properly mediated, the effect is not adequate enough for the stimuli. Conventional hard surfaces also differentiate the vibrotactile feedback, so they're not very effective in transmission of signal. And absorption and signal distortion is also rarely considered in designing haptic feedback for mobile devices. Therefore, we need a signal from the transducer to the point of contact and mediate the two effectively. Otherwise, the signal filtration, interference, or any other objectives basically could reduce the frequency usability and create dead zones either on the back of the device or where we're interacting with the device. Okay, so now we move on to what the paper basically discusses is that screen overlays. If we see that the touch screen itself or the touch points on the touch screen itself are the center of the haptic feedback, that is not how the mobile devices are designed these days. And the hard surface of the touch screen also is not very useful or conducive to the vibrotactile signal being transmitted wherever the transducer may be. So to effectively generate vibrotactile feedback on mobile devices, it is necessary to mediate the signal between the source and the touch points. Also, we have this interaction principle or the problem that most of the contact points with touchscreens can be anywhere between 50 to 250 milliseconds. So we need to be able to not only collect the signal, transfer the signal effectively to the skin contact so that it's sensed properly. So essentially, if we look at today's mobile devices, they already have some sort of screen overlays on them, either protective overlays or skins or whatever. If we can only utilize or redesign this screen overlay to not only protect the touchscreen, but also mediate the signals or haptic signals being generated, this can be much more useful. And we use this basic principle to take a common XOPC slate and we covered it with a transparent plastic sheet, which was adhesively bonded to the bezel of the tablet in such a way that there was a hollow section on the touchscreen itself. We injected non-polar transparent liquid, electrically neutral liquid into the pouch. So there is a deformable overlay on top of the touchscreen. And then we attach actuators on and inside this overlay and actuated various signals at different frequencies. With a sound meter, we measured the audio noise, while the piezoelectric sensor was attached in the center, you can see, measured the haptic noise, and we compared the two. We also utilized another exact replica of this setup without the liquid screen overlay. Like I said, we apply 3 frequencies across all the actuators that we listed. We've been using multiple actuators, which I won't go into the detail of because they're NDA and some of the partners requested that I don't discuss them. But AAC, Fukoku, as well as Highwave are our partners in developing these systems. So we used these signals over all the actuators for both the setups, and we measured the resulting haptic signals using the piezoelectric sensors and displacement sensors. And the data was converted to decibels and plotted against the sound meter data that we collected. And if you look at the results, we can overwhelmingly see that all the actuators in the setup, we were operated at different frequencies, were more effective in the haptic mediator setup. The haptic mediator was also able to transfer vibrotactile signals to the fingertip contact from the actuator with minimum noise to signal ratio without compromising signal integrity or signal creating attenuation of any kind. Haptic mediator acted as a silencer as well for the auditory noise so that it was more effective. And this was more visible for the actuators that produced deeper actuation as compared to surface acoustic waves on top of the touchscreen itself. And our results also show that system resonance and frequency propagation are critical terms that we need to consider while designing mobile devices or haptic interaction. And we also believe that because of the deformable structure of the overlay, our skin contact is more conducive or is able to feel the vibrotactile signal more effectively, and unlike the glass touchscreen surfaces that we have. Of course, we have still lots of things to do. We need to research more on this non-conductive, low viscosity liquid. And I haven't mentioned the name of the liquid or the chemical composition because we're trying to patent it, but we're experimenting with its viscosity, as well as how much volume it should have, what thickness there should be on the display as compared to the display size itself. And we're also trying to understand the liquid's viscosity with reference to the resonance of the entire system, how that affects at different frequencies with different actuators or transducers. And using the liquid screen overlay, we're trying to limit ambient noise or unwanted noise and basically using it as a low frequency filter. Furthermore, as you can imagine, inserting liquid on top of the touchscreen display can be a little tricky, so we're trying to make it as robust and as useful as possible for common uses. Okay, am I early? Okay. So basically, what I didn't cover in the original slides was the structure of the skin contact and what nerve endings we're targeting while we're creating those signals. Very basically, as maybe you already know, that finger contacts or points of contact have different mechanoreceptors that can be triggered at different frequencies and different pressures. And what we're trying to do is attenuate nerve endings or mechanoreceptors SA1, SA2, and at frequencies of 0 to 300 or 0 to 800, which are ideal for touchscreen-based contact. And unfortunately, while the environmental noise is between 5 to 800, we're still trying to get our results sufficient enough so that when you're walking or you're biking or you're in a car or somewhere, you're still able to feel the feedback without having to amplify the signal in any way. I'm basically done. If you have any questions or you're interested in further details, please go through the proceedings and my paper. And if you have any interesting future prospects or anything you want to collaborate, find me at the conference. Thank you.